this is a sort of slightly different perspective on geometric algebra. So hopefully there should be some good overlap with the previous one. But my own background, I started research into geometric algebra back in 1990. My interest was using it in real problems. I kind of had a bit of a weird career. I sidetracked a bit and worked in the games industry, so founded a company called Geomerics back in 2005. We did global illumination for games. I was kind of hoping to get lots of geometric algebra into it, never quite got there. And currently I'm back doing research and also working for a company called Monumo, which is an AI for engineering company. So thanks to them for allowing me to come to this event and paying for it, which is great. And inside Monumo, we are trying to use AI techniques to design more efficient electric motors, which means we need ultra-fast simulation, et cetera, all the other stuff you've heard about. Hence the interest in combining geometric algebra and Julia, which is something I'm promoting quite hard internally. Now, you're probably thinking, oh dear, he's from a company, he's probably got a product he's trying to push on us, and I do. This is it. This is the geometric product. This is the largest I've ever done it. Oh, cool, thank you. It should be one of the most sort of profound equations in math, but it's just not that widely taught. You've seen that there are various different notations for it. This is what I would call the classic notation. This is the Hestonese notation. I think it's a notation that Clifford would have used himself. The wedge dot is a modern thing. I'm not a fan, but you can choose your own notation. The reason we just use juxtaposition is that the geometric product is very much like matrix multiplication. Often it's identical to matrix multiplication. With matrix multiplication, we're just used to just slamming the things together. So this is how we tend to do it. The other thing that's kind of misunderstood here is that this definition can be read two ways. One way, the way you've just seen, is that this defines the geometric product in terms of this dot and wedge product. And that's the way it's often taught. That kind of presupposes that you've already met this wedge product, which a lot of people haven't. I teach geometric algebra to school children a lot, and they've never met a wedge product. Or if they have, it's an abusive notation for the cross product. The other way of reading this, which is the way I prefer, is that this defines the dot and wedge products in terms of the geometric product. And that's where you should start. That's the simple thing. So what I thought I'd do for this talk is, rather than spend too much time on the code, I'd actually quickly run through the way I like to introduce a subject to, often to sort of pre-university people. But I will go extra fast. I should also say, this is the second time I've been invited to MIT to talk about geometric algebra. Last time I was invited, I was given 2 days to talk. I've had to cram all that into half an hour. So this will be fast. So the first thing I ask people to do is just imagine that we could multiply together vectors. So pretend that your school teachers were all wrong when they tell you that there's no way to multiply together vectors. We're just going to invent some rules and do it. And the rules are, our product is going to be associative. Anything else doesn't make sense. There's horrible things to deal with. It'll be distributive over addition. And it'll have this fundamental property that when you multiply together 2 vectors, you get back the length of the vector squared, because nothing else really makes any sense. There's no other kind of number you could extract from that. But you also know that the sum of 2 vectors is a vector. So that means that a plus b all squared must also be a vector. Our rules are that this product's associative and distributive, so we can expand out the brackets, and we're left with this identity here in terms of things that we've decided are scalars, and this half of the product, this ab plus ba term. So what you do is you just rearrange that. And if you look at the terms on the right-hand side and draw a couple of triangles and use your triangle formulae, you find that this term AB plus BA turns out to be twice the length of A, length of EB times the cosine of the angle between them. So that means that we've rediscovered the dot product, the inner product, classic scalar product. And our AB plus BA is actually turned out to be twice A dot B. We've actually defined the dot product now in terms of the geometric product. We've only done half the work, because we can decompose our product AB into a half AB plus BA and a half AB minus BA. So we've now got an A dot B term and half of this AB minus BA term. So this is the new bit. This is kind of the magic bit the geometric algebra introduces. And to understand this, we need to be in 2 dimensions. 1 dimension isn't enough. So we're going to choose 2 basis vectors, E1 and E2. They both square to 1. They're unit vectors. They're orthogonal, so E1 dot E2 is 0. But now we have a new way of writing the dot product. It's a half AB plus BA. So that tells us that E1, E2 plus E2, E1 is 0. So E1, E2 is minus E2, E1. So perpendicular vectors anti-commute. And that's the whole essence of the algebra. Parallel vectors commute with each other. Perpendicular vectors anti-commute. If they're a mixture, you get combinations of both. And if you think about it, that makes complete sense geometrically. It captures all of the geometric information you could think of from 2 vectors. But this, in getting here, we've ended up with something new. We've got this thing E1, E2, which is not a scalar. It's a new thing in the algebra. It's actually a thing we call a bivector. If we now run through this product in 2D, just imagine we've just taken arbitrary coefficients for our vectors, A and B, and use the anti-commutativity property of E2, E1. We end up with the inner product we all recognize, and this thing here, which is the directed, that term there is the directed area, this magnitude of it, and E1, E2 is this unit bivector that holds the information about the plane the 2 vectors are in. And this bivector has a magic property. So we know that 2 orthogonal vectors anti-commute. If we just take E1, E2 and expand it out, we can get rid of the brackets, it's E1, E2, E1, E2. This is where you really, really don't want lots of wedges and dots and things. It's horrible. Very clean. We can swap E2, E1 with E1, E2, bring a minus sign. And now the E1s and E2s collapse down, and we get to -1. So we have, for no effort at all, we have invented complex numbers. And the kind of game I like to play here is, imagine if this was the first time you'd met complex numbers. You would immediately associate them with real 2-dimensional geometry. We don't teach complex numbers this way. We teach complex numbers from, imagine you want to solve a quadratic equation, and you've got some missing solutions, hence complex numbers, which is a terrible way to motivate them. Who spends their life solving quadratic equations? But we spend a lot of time actually messing around with geometry. This is a far better way to motivate complex numbers. It's just not taught this way because we teach maths in the historical order that things were discovered, rather than the order that kind of makes sense from our perspective looking backwards. We should also fire off a few thoughts that, well, if this is where complex numbers come from, they come from this real geometry. This means that everywhere you use complex numbers, in physics in particular, there is some real geometry going on there, and that has implications for quantum mechanics that I don't have time to discuss today. One further simple piece, so Cedric also highlighted the importance of these things. You can sort of say, okay, I understand vector space anyway, I've got matrix techniques. What's unique to geometric algebra? Where you uniquely use this geometric product? And the answer is rotations. So imagine we just do a reflection. That first operation takes a vector n, reflects it in the plane perpendicular to n. We can expand out the 2a dot n term in terms of geometric products, and then we get a nice cancellation down to this sandwich thing. This a goes to minus n. You meet these sandwich operations all over the place in geometric algebra. Right, 2 reflections is a rotation. This means a goes to minus nan, and then it goes to minus m, sandwiching that. We get m, n, a, and m. And this product, mn, is a new thing that we call a rota. This generates a rotation. This dagger is a symbol for reverse. Again, there are lots of symbols in GA, and not everyone uses the same one. It's a fairly standard one. Actually, in the Julia implementation, I just use dash for adjoint here. And this sandwich here takes a vector and rotates it. And this type of operation works in any space. Once you've understood this, you can understand all of Lie group theory, all of Lie algebra theory. It turns out that these rotas are exponentials of bivectors, so things I've already talked about. Those bivectors generate Lie algebras. Every Lie algebra can be represented in terms of bivectors. Every Lie group can be represented in terms of these rotas. So it gives you this immediate sort of route into quite sophisticated maths or sophisticated topics with fairly simple maths. If that isn't enough motivation for you to get into geometric algebra, it is currently going through a lot of new interest in the machine learning field. There's been a few papers recently. The geometric deep learning people have discovered that embedding geometric algebra into their neural nets is a good thing to do. There's a group of Microsoft Research in the Netherlands, I think, and Welling and Brandstetter have also come to the same realization. These are two papers I picked out. There's a whole flood of these in China as well. The Chinese machine learning people are really getting into geometric algebra now. So, as I said, there are lots of different ways of implementing geometric algebra, but my personal preference has always been this geometric product first view, and that reflects both my kind of philosophy about it, but also how I want to implement the product, how I actually want to produce a library for it. So I want to implement the geometric product and then drive dot and wedge products off that. And there's kind of two ways you can do this. You can use a blade representation where an object is a combination of lots of basis blades with magnitudes. Then you need to work out a product for the basis blade. Or you can use the matrix representations, which is kind of the core to what I'll talk about in a bit. But just running through the first approach, there's a nice little trick here that isn't well known. Typically, it kind of makes sense to work in what's called a balanced algebra. We've got equal numbers of positive and negative signature. That just covers every possible case. David Hesses likes to call this the mother algebra. It's just every other algebra kind of within it. And it has this really interesting decomposition, it's direct products of much simpler algebras, these G11 algebras. And the nice thing with this decomposition is that every block commutes with itself. So this kind of collapses the geometric product down into much simpler commuting units. And this gives us a very, very quick way of doing the blade multiplication. And I think this is a quite important idea that has not really been fully exploited. It gives us a slightly unusual representation for elements, but what I tend to do is you represent the basis blades as a binary number, 8-bit, 16-bit, depending on whether you want to work in 4-4 or 8-8, or so on. And each unit entry represents either E1, F1. The slightly unusual thing is that now the thing here that you might think would be E2 actually is E2 times a copy of N1. It's these additional copies that make everything commute nicely. The end result is that when you're trying to multiply together two blades, getting the resultant blade is easy. It's just an XOR of the binary numbers. Getting the sign is the tricky part, but this collapses the calculation down into lots of single units, and you only get a minus sign in the case where the first entry contains an F, and the second entry is a vector. And there's a couple of very nice little binary operations that do that for you. You just do an AND with a binary representation up there, and for the second term, you just do a shift left and an XOR, and then you do you count the ones in the result. This was a big thing for me because my original journey to Julia took me via Haskell, and I'd done a lot of this implementation in Haskell, and Haskell has no way of accessing the raw kind of binary command. So this part was incredibly slow because I was kind of doing it all with actual numbers. So I got a sort of massive speed increase just from porting from Haskell to Julia, and I will not be going back. So that all works fine, and it gives you an approach that's quite like the one Cedric described, except he's kind of intercepting the stuff a little bit further downstream. But there is an alternative way of thinking about geometric algebras, and this has some useful optimizations in it, particularly for the geometric product for things like rotors, because by using these underlying matrix representations, you take advantage of the fact that certain products automatically cancel out. So you reduce the amount of computation you have to do in some cases. This table was something that was worked out in the 50s, I think. People have been through and they've classified every possible geometric algebra and worked out the matrix representations. You only really need them for size up to total dimension of 8, because beyond that they repeat. And inside here you get representations which are tilbity matrices over the reals, quaternions, matrices over complex numbers. So you build up your geometric algebra from combinations of reals, complex numbers, or quaternions. You can't escape the quaternions here. In fact, they turn out to be ubiquitous. But that isn't the complete story. It's very easy to go in and implement those products. Oh, a bit better than I thought, thank you. But that doesn't give you something particularly optimal. There are some tricks. These tricks are already talked about for sort of decomposing products. And this particular identity here is this periodicity thing that says that once you've got up to 8 dimensions, there's nothing new to be found. But it's this identity here is a really interesting one, the top one. If you take a geometric algebra, the dimensions of each element is given by the binomial element. So you've seen 1, 2, 1 for 2D, 1, 3, 3, 1 for 3D, etc. And every element has a grade. So scalar is grade 0, vectors grade 1, bivectors are grade 2, trivectors are grade 3, etc. Just a number of those E elements in there. But it turns out if you take an algebra and just pick out the even half of it, that is also a geometric algebra in its own right. And there's a particular way of going between them. But it's a geometric algebra of half the size. So you've halved the size of the matrix representation for it. And it turns out there's a lot of power you can get from that, because we don't need to use the full fact representation of each algebra that we want to implement. We can use this representation of the even subalgebra and use a few tricks. What we're going to do is find a canonical map between odd elements and even elements, which is usually the algebra kind of naturally suggests that. We're going to form the matrix representation of just the even part. And then we need to implement 4 products rather than 1. So it's a little bit painful in the code, but the interface is very nice. You work out even, 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 odd, odd, even, and odd, odd. And usually they're all roughly the same. And to implement this, there's a bunch of kind of design considerations that I went through, being round and round, trying to find the simplest, cleanest implementation. The geometric product is implemented by overloading the star operation, multiplication. Nothing else, to me, makes any sense at all. I would not want to introduce a new object for it. Star is a thing we use for matrix multiplication in the linear algebra package. And in fact, the way I've structured things, I'm assuming the linear algebra package is there anyway, because if you're doing anything geometry-like, you've probably installed linear algebra. And the remaining things most of them I've just borrowed from linear algebra, just overloaded the functions from there. So geometric products, a star, makes the code really, really easy to read. You need an operation that projects bits out of a multivector. So you need something that says, I've got an object, but I just want the vector part of it. Project mn, so n would then be 1. That projects out the vector part of m. So you need to implement that. You also need some way of getting numbers sort of out of the geometric algebra. You need some way of getting scalar numbers out so you can actually put them into somewhere else in your program. And there are 2 commands that, again, that just overloaded from linear algebra. Trace m picks out the scalar part. I used to call this sort of scalar part a SCP, but actually just using trace makes sense. It's not exactly the same as the trace of the matrix, because it's a factor, but it's the same basic concept. It's taking the scalar part out. And this is one I've wrestled with a lot, and I'll be happy to be told that it's a bad choice. A key operation in geometric algebra is taking 2 things and multiplying together and picking out the scalar part of that. And I've used dot for that because that is exactly what the linear algebra package does, with a caveat that dot does mean something a little bit different sometimes in geometric algebra, because we talk about an A dot B meaning something slightly more general as a product. So in the documentation, I don't use dot there. I use inner for the inner product, not dot. This may be a mistake. It can be changed, but it makes the parallels to the linear algebra package as simple as possible. And then the one actually I really like is the reverse operation is just a tick. It's the same as you use the linear algebra package. So this makes the code really easy. So I'll just walk through one example implementation. Just the 2D case is sort of simplest one. The even subalgebra of the 2D algebra, which is scalars, 2 vectors, one bivector. Well, we've already seen that bivector squares to -1. So the even part of it is the scalar and something squared to -1. So obviously its representation is complex numbers. In fact, I'd say this is where complex numbers originate. So we only need to represent things as a complex number. Okay, so that's really easy. And this is sort of this is part of what the code then looks like. We define an even object, which is just complex number, just a placeholder for that. And the odd object is also a complex number because the representation is always the same. The map between them is multiplied by E1. In case you're wondering, well, what's this special E1 vector doing there? Actually, if you think about complex numbers, it does make a lot of sense to pick out E1 as a preferred direction because we would think of that as the real axis. So it's fairly naturally picked out. And then we just go through and work out what the product should be. So that just means taking care of when there's an E1 sort of sitting in the middle. So we just overload the multiply operator. When you've got two even things multiplied together, you just multiply the complex numbers. If it's even and odd, you've got one of these E1s in the middle. When you take that back to the left, it puts the complex conjugation. So you have to put a conjugation in there. Odd even is fine, and odd odd, again, has a conjugation in. Reverse is easy to work out. For the even ones, it's the conjugate. For vectors reverse themselves, there's nothing to do there. And then a few bits of code to overload the trace and dot operations. There's a few other things you add in. I haven't shown the project one, which is a tiny bit more complicated. And then you just go through and implement that for all the various algebras you like. So it's a sort of boilerplate template code, but then each specific algebra has a special implementation there, which is a bit clunky. It's not the way I like to talk about GA, but it gives you a very, very efficient runtime library. Another quick example, I won't go through the code here, is 3D. We've already had questions about 3D. In 3 dimensions, you've got scalars, 3 vectors, 3 bivectors, 1 pseudoscalar. All 3 of those bivectors square to -1, and they have a sort of ijk equals -1 type relationship. So they are the quaternions. Again, quaternions were discovered, invented, depending on your view of maths, about 10, 20 years before Clifford's algebras were. It could very easily be the other way around. In fact, what Clifford was trying to do was just generalize quaternions to other spaces. But to my mind, quaternions are just part of the subject of geometric algebra, Clifford algebra. So we just need to implement a quaternion product. I implemented my own, though there's actually a perfectly good quaternion library in the Julia ecosystem. But because of some of the choices I made, I needed to change a couple of things in that, so it's just implemented. And then you implement a quaternion product. The map between even and odd elements in odd dimensional spaces is really trivial because it's just multiplication by this pseudoscalar, and that commutes with everything. So it makes the implementation really easy. You just need to make sure a couple of signs are correct. So the implementation here is your even subalgebra is the quaternion algebra. So E3, E2 maps to I, E1, E3 maps to J, E2, E1 maps to K. And then odd elements map to even elements by multiplication by I. And the pseudoscalar commutes with everything. And this makes the final code very, very simple and also extremely efficient. So this can do, on that laptop, rotations in about 40 nanoseconds with that sandwich operation. The equivalent 3x3 matrix thing actually takes longer, which is a bit odd because there's kind of more multiplies. But actually, when you're really down at this nanosecond thing, you care more about allocations rather than number of multiplies. But this is extremely fast. It's enough to build really kind of robust numerical work on top of. I've just got time to give you one quick example of a problem I solved recently with this. In electromagnetism, you have lots of elements seeing other elements. Very similar thing in graphics. You often want to compute the solid angle of a triangle from some origin. So this is the GA code to do it. The solid angle you get by projecting each vector onto a sphere, and then you need to work out the area of the spherical triangle. A nice way of getting the area of a spherical triangle is to use something called holonomy, which is you take a vector and you parallel transport it around, and you see the angle which hasn't gone back to itself. So you just need 3 rotors to do that movement around the sphere. So this sets up the problem. We take in our 4 vectors, y is the origin. We create 3 unit vectors from y out to x1, x1, x2. This one line here creates all of the rotations and multiplies them all together to get the final rotation that you get by going all the way back. It does it using a very nice property of rotors that when you multiply together A and B, that gets you a rotor, but it's a rotation of twice the angle you want. If you want to square root it, you just need to find half the rotation between that and the identity. And the way you do that with rotors, you just add them up, and then you normalize the result. So this is a very, very simple way of getting the rotation. We don't actually even need to normalize the result, it turns out. But having got that rotor, normalized it, and then you just take the bivector, the magnitude of the bivector part of this, which is this projecting it back into the A direction and then taking a log to get the angle out. It does, that's a really kind of nice, elegant way of getting the solid angle. But geometric algebra is kind of full of this stuff. You saw from Cedric that all these complicated intersection algorithms and joining operations that you meet in graphics, very, very elegantly expressed in GA. Okay, so just about ready to wind up. Whenever I talk at these type of events, I always hope there's someone from a hardware company present or listening, or at least someone who has the ear of a hardware company, because a question I often get asked was, how could you implement geometric algebra in hardware? What do we need? And for a long time, I was kind of really obsessed about this blade product thing I talked about earlier, thinking, well, it'd be really nice if we could do that. But the problem with that blade product way of working is you end up with an array as your result, but you then have to do lots of sorting to get it back into a canonical order so you can do products the right way. It's not very elegant. But if you turn around and think, well, what are the algebras we actually use in practice? What are the ones that are getting the most interest at the moment? 3D, obviously. That's how we do rotations. Quaternions are a core part of lots of game engines, for example. G40 is used for projective geometry. This is kind of classic projective geometry, stuff that OpenGL is based on. It turns out the implementation of that requires a pair of quaternions. That's the even subalgebra of that. This one here, G301, is the one that's currently called plane-based geometric algebra, which is getting quite a lot of interest at the moment. Again, the representation, the even part of that, just requires a pair of quaternions. And the fourth one that's getting a lot of interest is this one that's called the conformal geometric algebra. This is the one where spheres, circles are all primitives. This requires 4 quaternions. It's actually a 2x2 matrix of quaternions, but rather than impose a matrix structure here, it's easier just to unwrap that. But in all cases, it's just quaternions used in different ways. So my answer now to hardware companies, whenever they say, what can we do to enhance geometric algebra implementations, is just give us quaternions. Just make the quaternion multiplier as fast as you possibly can. It's a real shame that SIMD just doesn't quite do that at the moment, or the CPU SIMD. But with just a few tweaks, you could easily make it a lot faster. So, yeah, summary. This type of matrix implementation is actually a very good way of making extremely fast GA operations for small algebras. It does not work for big algebras because you can't, that type of product expands out quite badly. And if you're up in, say, 64 dimensions and try to store a rotor, there isn't actually enough storage on the planet because of the bloated space you get. So you have to come up with different techniques there. But for small algebras, this is definitely the way to do it. The way I think about all library implementations is that you just want a product, ideally star, a projection on the grade operation, an operation for getting the scalar part out, and a reverse operation. Everything else you can kind of build on top of that. So it makes it a very, very clean interface. The library is currently available there, but there's a little bit of a hiccup with the registration process that I think there's a name conflict you just need to sort out. And finally, yes, the library's there. Contact me any way you like, though the Twitter handle there is more for historic reasons and because of any active use these days. Thank you to the organizers, and also thank you to Monumo. If anyone is interested in talking about AI for engineering, we are recruiting. Come talk to me afterwards. Thank you.
Thank you very much, Chris. We don't have time, but since there is a quarter until the keynote, let's take one question if there is someone that wants to ask something.
So can you share your experience in migrating like existing code that's not very geometric algebra aware to using geometric algebra? And in particular, code that's not mixing, for example, by vectors with scalars, and how to do that efficiently?
Good question, actually. I've never done that because all my life I've worked in geometric algebra. I'm a bit of a corner case like that. I think like all kind of code migration, you need a good reason to do it. If the code works, then leave it alone. The main reason you'd want to, say, port to geometric algebra is because there's a better algorithm you can take advantage of, in which case you're not really porting, you would be rewriting largely from scratch.